Hello, everyone. Welcome to the second video on Bayesian deep learning. This time we'll be talking about priors. So here again is the Bayes rule as we'd implement it for neural networks with our likelihood and our marginal likelihood. As I already said, this video will be about the prior right here. I think a nice quote about the prior is from Michael I. Jordan from the Machine Learning Summer School in 2017. If we have garbage in, that is arbitrary priors, then we get garbage out, that is uncontrollable error bars. And so the simplest and most common prior, and also I think the first prior ever used to find a Bayesian neural network, is the normal prior. And as we talked about in the last video, the simplest thing we might do is for every particular weight in our weight matrix, we'll just set a normal distribution as its prior. So just one univariate density function applied to every weight in the weight matrix. And these would be independent. There'd be no kind of structure or no information sharing across weights. And while simple, normal priors have a interesting property in that they become, is that they cause a neural network to become a Gaussian process as the hidden unit becomes infinite, as the number of hidden units goes to infinity. So if you're not familiar with a Gaussian process, it's a highly flexible Bayesian non-parametric model that defines a prior over functions. And so I show a clip here from Wikipedia, where here is some function sampled from a Gaussian process prior. Here's the Gaussian process posterior, and here is the resulting predictive distribution. You might think that sounds great. It sounds kind of confirms what we might have already thought, that these neural networks can become very flexible Bayesian non-parametric models. However, Radford Neal in his seminal thesis on Bayesian neural networks pointed out that this might actually cause a problem, or might actually take away from the spirit of neural networks, and that they will not learn hidden features. And to quote him, with Gaussian priors, the contributions of individual units are all negligible, and consequently, these units do not represent hidden features that capture important aspects of the data. I'll refer you to his thesis for more information on this, but it basically comes down to the smoothness requirement. If we think about how the function will change with respect to an input, Gaussian priors don't allow the model to make kind of drastic changes as the input changes a bit. And so we'll contrast this behavior to jump process priors that we'll show later. And this convergence to a Gaussian process happens much faster than we would might expect, and we don't have to go anywhere near an infinite number of hidden units. So here's a nice investigation of this phenomenon from Matthews et al. 2018. And on the x-axis, they show the number of hidden units per layer in a network. And on the y-axis, they show the maximum mean discrepancy distance from a Gaussian process. And the different lines are one neural network with one hidden layer, a Bayesian neural network with two hidden layers, and three hidden layers. And we see that for one hidden layer and just maybe 5 hidden units, we actually start seeing converging to a GP. And so this red line marks when it converges to some GP, maybe not the target one that would correspond to the infinite limit. But we see actually corresponds to some Gaussian process. And it converges to the true infinite limit in, maybe 20 to 30 hidden units. Adding depth to the neural networks, when we see we go to 3 layers, it delays this onset. And so it only converges to some GP after 10 hidden units. Okay, so that was normal priors. And so now we might say, okay, well maybe let's change the behavior a bit. And instead of having factorized normal where we have independence between two weights, W1 and W2, we'll actually introduce some covariance structure such that the two weights will depend on one another. And so, yeah, what we showed before, independent normal priors, that'd be equivalent to having just zeros on these off-diagonal terms. But instead, we want to put something there. And we think about how neural networks work, you know, inside the hidden layers. We'll have all of these hidden units in a particular row applied to the same dimensions of the hidden representation, assuming a right matrix multiply. That means if we want the neural network to actually use these hidden features, we'll probably want these weights to be correlated. That is, when one of these weights goes up, we probably want the others to go up as well, because that will mean that this corresponding hidden unit that's kind of tied to here will be an active feature. And so we can do that in the prior by simply taking the weights that happen to be in the same row. Say it's maybe just these two for the sake of kind of simplicity. And then we would have a positive off-diagonal element. And that would give us the corresponding behavior that we see here with positive correlation, such that when W1 goes up, W2 goes up as well. And when W1 goes down, W2 goes down as well. We can induce further structures still across priors by using hierarchical priors. And so that is, instead of just having a prior in the weights, PW, we actually give that a prior itself. So we give the prior some parameters tau, and we put a prior on tau as well. And so we add it to another level to the Bayesian hierarchy. And so, you know, a common way to do this is with a normal distribution on the weights again, and perhaps zero mean and some variance tau squared. And so how we might want to choose this for several reasons. So the first might be to give a structure. And so again, thinking of how the matrix multiplies come about in the hidden units of a neural network. Again, we might want to attach a scale here, call it tau I, to each of these rows, such that with using the same logic as the multivariate normal, when one of these features is active in this row, the whole row of weights should become active as well. Or if they're not, the same scale should be able to shrink, essentially turning off that row and corresponding dimension of the hidden units. So this prior is actually called the automatic relevance determination prior, developed by David Mackay and Radford Neal back in some of the early work in Bayesian neural networks. And it's called automatic relevance determination because it can automatically determine the relevance of the hidden units. In that, again, if the corresponding hidden unit for this dimension is determined to be irrelevant, we can shrink its contribution across contribution by turning all of these weights to zero, or shrinking them to zero according to the scale. In addition to structure, hierarchical priors are also good for inducing heavy tails. And so one simple way to do that is, or to see that, is if you had an inverse gamma prior on the variance, and we integrated this out to get the marginal prior on the weights, this would correspond to a student T distribution. Right? So it's like an infinite scale mixture. And so this is one elegant way to represent the student T, because we don't have to represent it with the heavy tail distribution directly, but we can represent it in this composite form. A distribution that's even more attractive than the student T is something called the horseshoe. So again, we have the same normal prior on the weights, but now we put a half Cauchy, that is Cauchy just on the positive values on the variance. And this gives us the distribution in red shown here. So a normal 0, 1 is shown for reference in black, and the density function of the horseshoe is shown in red. And so we have much stronger peak at 0. So this will shrink the weights a lot harder to 0 than a normal prior otherwise would. But also it has heavier tails as we move away from 0. And it's, the density function is actually higher than the normals. And so why is that good? It gives us something called bounded influence. And so consider this little simulation where we just have one data point shown in Y here. And we have 3 priors, a flat prior or improper uniform prior, a Laplacian prior, and a horseshoe prior, all centered at 0. And on the y-axis, we have the posterior mean of this one data point. And so we see that for a flat prior or no prior, the posterior mean is simply equal to that data point. And that's why we have a straight line here on the diagonal. But if we have these priors like a Laplacian or a horseshoe, we get some shrinkage effect. That is, if y goes away from 0, it'll be pulled back towards 0 by nature of that prior being located at 0. And so we see for the Laplacian or horseshoe, as we deviate from y equals 0, our y value still stays around 0 because of the shrinkage effect. But as we move away sufficiently, we will start to deviate from y equals 0, the 0 line. Why heavy-tailed priors are good is that once you deviate far enough from this, from the region around where your prior is located, that probably means that your prior is just bad. It's not actually helping you anymore because there is strong signal that value should be away from 0. And so ideally what you want then is for the prior to quote unquote turn off. And the horseshoe does exactly this. So again, the horseshoe is in blue here. We see that once the y value gets sufficiently far away from 0, out to like 10 here, it is able to converge back to the improper prior, or that is the flat prior, back to the diagonal line. Whereas the Laplacian always has to stay it's kind of holding us back, and that is it's keeping us from converging to a maximum likelihood estimate or converging to the flat prior. Right, so it's having some effect out here, even though there's strong evidence that the kind of zero-centered assumption is wrong. It's not on here, but a normal distribution would be even have this effect even stronger. So it'd be something like out here. And so this ability to kind of forget regularization or turn off regularization is called bounded influence, where we want our priors to have bounded influence. That is, if there's signal in the data that we should kind of leave the area around 0, then our prior should let us do that. And so the horseshoe prior is kind of a gold standard for robust regression, and hasn't found wide uses in Bayesian neural networks, but there's good evidence that it does help when you can use it. Another nice property of these heavy-tail priors is that they break the Gaussian process convergence that I talked about before, in that they actually do allow the neural network to learn hidden features. And so we see this by plotting the samples from models with heavy-tail priors. And here I show 3 different sample functions for a student T prior with 10 hidden units, 1,000 hidden units, and 100,000 hidden units. And we see that in all of these functions, there are these big jumps here. Right? And that is because these heavy-tailed priors induce a jump process prior instead of a Gaussian process. And so we can see that even though we go to this infinite limit, small changes in the input can result in drastic changes in the output function. And that is, we can think of like a hidden unit or a hidden representation kind of turning on and kind of putting us into a new type of function class. Okay, to switch gears almost entirely, we can move from these continuous priors that we showed before to discrete priors. And so you might say, okay, well, I just want to draw my weights. I just want to let them be binary. We can draw them from some Bernoulli distribution. And this is interesting because discrete priors have computational efficiency, because right, we can just store them more easily and do the arithmetic more easily. And they also actually have a biological plausibility as well. But the major downside is that we don't really have access to gradients. We can't train them as easily. Okay, so far we've just been talking about feed-forward neural networks. We'd also want to think about other architectures. And so say for a simple modification, we just add skip connections. That is, we have a residual network where we have skip connections that add the previous hidden layer into the new hidden layer computation. Right? That is, we have HL plus 1 equals F where this is our residual connection. And this is our usual nonlinear transformation. So when we think about how information flows here, that the hidden units can actually bypass the weights here by nature of the skip connection. And so if we think about what this means and how we might want to kind of regularize a neural network, that means we could add a shared scale across the whole weight matrix here, W. Right, so that would give us all the weights in this matrix a shared scale. And posterior inference could then learn to shrink that scale. So if it shrinks that scale, it essentially removes that layer from the neural network. And so then we have, and going back to our equation, we would essentially have h of L plus 1 basically equals h of L, because this term went to 0. And so that is a way we could use Bayesian priors to control the effective depth of the residual network. And so implementing this, we would have for all of the weights in one layer, so where L index is the layer, I and J the row and columns, we'd have a shared scale gamma here with the L index. And we could also turn on both automatic relevance determination and this whole layer scale prior. And so that would allow us to control the width of the neural network for automatic relevance determination via tau, and the depth via gamma. We can also apply the same logic to convolutional layers. So in convolutional layers, the natural resolutions that we might want to set priors are the filter group and the channel group. And so every kind of colored blocks here represents a region that you might want to set a shared scale. Right? So you might have a shared scale over each channel and over the whole filter group. We can think of a similar principle for LSTM RNNs, where W represents the input parameters. We might want to have a shared scale over every row. So that would allow a given dimension in the input vector to be effectively made irrelevant, or some sort of feature selection. But for the recurrent parameters, maybe we want to kind of turn off that scale sharing, because once we think information makes it into the recurrent network, it is then deemed useful, and so we don't want to do any strong regularization of the current parameters. Of course, this is just one example, and other applications might dictate to have shared scales across every input weights, or even the recurrent parameters too. The important idea is to kind of think about what is being multiplied together and what sub-modules of the network might you want to shrink with the Bayesian shrinkage via the scale. So obviously you might say, okay, I don't know the prior, but I want to tune it in some ways via data. And you can do that by type 2 maximum likelihood estimation. So if we have our prior P of W and we have the prior parameter psi here, we don't want to tune it via just the map or maximum likelihood estimation. We actually want to use the marginal likelihood. And just to remind you, the marginal likelihood is when we take the likelihood and integrate out the prior. And that just allows us to see the direct effect of psi across all possible values of W. Unfortunately, as you might guess, doing this integration is extremely hard for neural networks. I just showed one W here, but we'd have lots and lots of W's and have a very high dimensional integration problem. And so this is an active area of research. And so for one instance, you can, I'll refer to this recent paper, Scalable Marginal Likelihood Estimation for Model Selection and Deep Learning by Immer et al. So just to wrap up, a summary. Normal priors are the most common priors you'll see for Bayesian neural networks. And they're easy to implement and they correspond to Gaussian processes in the infinite limit. Hierarchical priors might be often a better choice. They're good for inducing structure and heavy tails, but they require a little more inference because now we have to do Bayesian posterior inference, not just for the weights, but probably for those scale variables as well. And I also mentioned discrete priors, how they kind of have some nice attractive properties like efficiency, but they're hard to implement. If you want to read more about priors, I'll give you some references. You can read Priors for Neural Networks by Herbert Lee. This is an older reference from 2004. In chapter 3 of my PhD thesis, I have a survey of neural network priors. And then Vincent Fortown has a more recent review called Priors in Bayesian Deep Learning, a review. So please check those out. So now that we've covered priors, in the next video, I'll be talking about posterior inference. That is, how do we actually fit and get the posterior of a Bayesian neural network?